Okay, so over the last few weeks, I've been in New Zealand and rekindle, I suppose, my desire to do something absolutely from bare metal up on neural networks. I suppose to some extent triggered by ChatGPT and knowing that somewhere deep down inside is just simple bits of mathematics emulating how the brain works. Not that I expect to be able to build my own ChatGPT from scratch on an ESP32, mind you. Bruce Farthing. Bruce. G'day, Bruce. We just started off, so you haven't appeared yet. So these neural networks are the basis of most of the artificial intelligence that we're seeing. Historically, that's not been the case. I read quite a bit of the history as well, which I haven't made any slides for, but I remember back in the late 70s, I got my first TRS-80 computer. And one of the things I played with then was a supposed artificial intelligence program, which, and I forget the detail, but it had some sort of factor relationships between objects built in. It was a sort of tree search structure, and you could put assertions in and it would dig out the answer if it already knew. And if it didn't know, you could tell it, and then it would know in future. And that particular direction in AI turned out to be a complete dead end, ultimately. But earlier than that, even in 1959, this will come later on actually, but they'd started playing with the idea of neural networks too. And it was people coming from an interest in how does the brain work rather than wanting to create an AI at that stage. And there was one guy who made a thing using literally motor-driven potentiometers and feedback to correct them. It was never terribly successful, apparently. In the, I guess, 80s, there was a guy in Cambridge by the name of Geoffrey Hinton. He's my current hero. And he perceived that the neural network approach to AI would ultimately be able to be very productive. But he went through many, many years out in the desert where his fellow researchers were laughing at him because they thought it could never happen. But for Geoffrey Hinton, and I think there's an interesting bit of history, the concept of using neural networks and multi-layer networks and deep learning, it became possible when computers became powerful enough and there was enough data on the internet to mine for teaching these AIs what to do or how to do it. So for Geoffrey Hinton, the problem was not a matter of capability, theoretical feasibility. It was simply a matter of scale, that before 2008, he was not able to make anything with enough grunt to do the job. And it was not until 2012 that he and his fellow researchers had a breakthrough and got something working, which was pretty impressive. And they held an auction. Long story short here, they held an auction. They sat in a hotel room in Vegas or somewhere like that for about a week, holding a silent secret auction by email. And having formed a company, sold their company for $22 million to Google. And he actually opted for Google. At the end, he said, no, I'm going to sell to Google. The Chinese were also in it, but he decided to sell to Google. And then, of course, worked for them for a long time. So quite an interesting history. So much of the stuff that we're seeing, and you were saying before, George, that it's amazing how fast ChatGPT is evolving.
Yeah.
None of this shit existed before 2012. Consider that. And ChatGPT, by the way, has been around, existed for about 5 years. It's just that late last year, they finally made it public. And some of the insiders think it was done prematurely. Of course, then all the arguments start about ethics and killer robots and all that stuff, which is to be expected, I suppose. So it's actually very new, very, very rapidly evolving. The other thing I've come to realize is that there's no kind of hard and fast theory about how it works. It's a lot of it, I get the sense, is people just saying, hey, let's try this and let's try that and see what works best. You can't sit down and analytically design the best neural network for a job. It's too complex.
Yeah.
So it's a suck it and see thing. And when they do work, no one knows exactly why they're working or how they're working, which is fascinating. Anyhow, so this little diagram here, which I picked off the web, a neural network is something, this is very, very simplified representation. In fact, this is one single artificial neuron, if you like, on the right and a real neuron on the left. It has a number of inputs to it, which might be light intensity from receptors in your eye, or frequency, different frequencies from your ear or what have you. And within one neuron, the inputs are which come in here, 0, 1, 2, what have you, up to, can be a large number. Each one is multiplied by a constant multiplier, which in the brain can vary with learning, and in a neural network can vary with learning. And then they're all added together. And ultimately, if it all adds up to enough, the neuron will fire. You've probably all seen and heard the sort of neuron firing, click, 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 click type of stuff. There's always a threshold. Below the threshold, it doesn't fire. Above the threshold, it does. And by changing these weights here, you can change the pattern of inputs that it will respond to, essentially. Now, having said all that, big warning here. Oh, isn't it wonderful? Don't you love the technology? It's meant to do it that way. Big warning. Who's heard of the Dunning-Kruger effect before? It's one of my favorite psychological phenomena. It's when somebody knows a little bit about a subject, they suddenly think they become an expert and start spreading their expertise around with gay abandon. So just a warning, I'm not an expert. There's probably a bit of Dunning-Kruger effect in here. But I guess if you know nothing about this beforehand, then I'm a cyclops in the land of the blind. The one-eyed man is king. So take everything I say with a pinch of salt, and if it really interests you, go off and do your own research. Google is your ChatGPT is your friend. Okay, now the ultimate ambition for me, with my total hobby, doing it just for the fun of it, but right from scratch on bare metal, is to be able to make a little machine that will sort Smarties. Do you have Smarties in your hometown, Iqbal? Or do you have M&Ms?
It's got a Bengali name. It's called James.
Okay, there you go. A Zane's sorter machine. And here's a nice little pile of Smarties I found on the internet. Use a little program to remove the background. There's a little utility for doing that, by the way, very useful. And to sort the different colors into different bins. This is vital stuff. Smartie sorting really is an important thing. So that's the ultimate outcome for what I want to do initially. If I get more ambitious, I might be able to do recognition of output from a camera or something like that. Hook up an ESP32 cam and read something.
To me, that's quite ambitious. There's an awful lot behind this.
Yeah, but I'll eat an awful lot of Smarties in the process, George.
Well, it's got some side benefits.
It's getting a bit hot in here. Excuse me.
So the side benefits present in profile.
For what, sorry?
The side benefits of Smarties eating present in profile.
Yep. Okay. So that's the ultimate goal for me, and I tend to think of everything in terms of what would I do for sorting Smarties. I don't know why my down key suddenly isn't working. Page down. Okay, I'll just scroll down. So back in 1959, this guy came up with something called a perceptron, and it's a term that still exists and is used somewhat interchangeably with neural network. Just doing a bit of research today, I found that there is not a broad agreement on the distinction. So it's a bit of a Apple versus Windows versus what have you kind of a debate, which I'm not really going to buy into. But if you imagine that you have a test Smartie, a color sensor that will produce a value for red, a value for green, a value for blue. You can buy one of those off eBay for $5, or I will probably make my own because there's a bit of fun in that as well. And then you have a red multiplier. I've used a potentiometer because we're all electronics type people here. A green multiplier and a blue multiplier, which go into this thing, which is a summer, and got what's called an activation function. And if these potentiometers are set to, they're metaphorical pots in all probability, though that guy back in 59 used real potentiometers. If they're set to the right set of values, the turquoise light will light up with a turquoise Smartie, but not with a red Smartie or a green Smartie or a blue Smartie. You just have to, just using that word just very lightly and loosely there, you just have to get these coefficients right, and it will happen. That would be for a single color. For multiple colors, of course. Oh, a couple of other things too. So there's a factor in there which I don't fully understand, but it's called a bias, where you add a constant into the sum to start with. It might say everything is scaled to between 0 and 1, which is probably the most rational thing. Then that bias might be 0.4 or 0.5 or 0.6. As far as I can tell, you just fiddle around till you get the best results. There's no kind of magic rule for how you do it.
That might be noise cancelling.
A big fun?
That might be overcoming the noise floor.
I've no idea. Spoken like a true RF man. You're still trying to
Everywhere you go, there's a noise floor.
You're still trying to pull femto signals out of the atmosphere from Indonesia or whatever it was?
Oh no, I figured out that I should have realized a long time ago it was impossible.
Oh, okay. So then the other thing is this activation function. In my readings, I came across something called a sigmoid function quite a few times, which seems to be popular. And then I came across some stuff that said, "No, you don't use that anymore, mate." So again, it's a kind of a suck it and see affair. But the point of this function that takes the output of the sum and then transforms it through the function must be nonlinear. I don't know why that's the case, but it is the case. And the very simplest one that I found was basically output equals x if x is greater than 0, and output equals 0 if x is less than 0. But that will depend on how you're scaling your numbers, of course. And then someone else said, don't have a flat section here, because if that section is flat, if you wander into that during training, you'll never get out. It's the valley of death. So I've just depicted that as a slow slope and a steep slope. And presumably when you're beginning to actually tune into the color you're looking for, you're going to be coming up there on the slope somewhere.
Isn't that just a comparator, David?
It could conceivably be just a comparator. I have seen it depicted just as a right angle, straight along and then straight up. But this
That's where the B would be the reference, presumably, for the comparator.
No, it's added in there. It's an the bias is an offset. But I think it's better to not try and overthink it, John.
Right.
Again, from my Dunning-Kruger point of view, Don't overthink it. Because look, once I get free of the project I'm on, I'll be building this in software and I can tinker. And I think an ESP32 has got enough grunt to do sort of level of stuff I want to do. So then eventually you get an output. Now, for a single thing like this, the output is more likely not to also be a function, a variable amount of a variable number, not just an on-off.
Right.
But again, even that can depend. If you're yeah, that can also depend on what it's being used for and how it's being used. Again, a little vague. I'm sorry, I'm still vague on it myself. So now we want to sort multiple colors of jelly beans. So in effect, we need one of those gadgets for each color. If there's not enough here, there's more than 4 colors in that pile of jelly beans. I might have to restrict myself. Look, eventually I'll probably start with 2 colors. Hey, that'll be something, wouldn't it, to sort out green and red? Or
David, this is going to fail because these things are not jelly beans. You're talking about jelly beans.
Smarties, M&Ms, whatever they got in.
Okay, sorry,
Yeah.
being pedantic.
It's a
They may also
precision
be,
game, David. Precision is everything.
yeah, probably there'll be 3D printed little discs of different colors. Who knows?
All
David,
right.
it seems there's Smarties in every corner.
Oh yes, yeah. We'll have to get a dog to clean them up again, I think. So well, yeah, ultimately you would need to have effectively 1 channel per color. Oops. Now I'm going to define the error function. So each of these numbers should be as close to as possible to the ideal number for the color being detected. That's a red one, that's a sort of yellowish one, that's a brownish one, and a bluish one. Ideally, maybe the ideal number might be, I'm going to say 0.9, I don't know. But for each of these, for any setting of the potentiometers, and for 1 Smartie in front of the sensor, the error function is numerically the difference between what you're getting and what you should be getting, what you want to be getting. So if you take the errors for each of these, square them all and add them up, that becomes the error for the whole network for a given input and a given set of settings. Does that make sense?
How do you know what the optimum is supposed to be?
Because I would know I know that this I take that one. I know that one wants to fire on red. So I know if I've got a red jelly bean there or a red Smartie there, then I want this one to be at maximum and preferably want all the others to be totally at 0. In fact, that's the training data. The training is to stick a red Smartie there and say you should be giving maximum output here.
Mhm.
So let's say the ideal output is 1, number 1. And in fact I've got 0.8 on this, I've got 0.2 on this, 0.4 on this, 0.7 on this. And for all these, the ideal output would be 0, of course. So for these, I've got 0.7 squared plus whatever it was squared plus whatever it was squared plus the difference between 1 and 0.8 on this one squared. I'm sure you're familiar with the sum of the squares of numbers because you square it because it doesn't matter whether it's a plus or minus error, it's still an error. You can use absolute values if you like. Does that make sense? Oh, I'm seeing an awful lot of no nodding here.
So to determine your best number for red, you'd have only a red there, so that the yellow, brown, and blue should have had ideally 0,
Yes.
and the red should be 1. Is that where we're coming from?
Yes. Yes.
Okay.
If the thing is scaled such that 1 is the golden number,
Yep.
It could be 10 million, or it could be whatever it is.
Okay, so you're seeing the ability to detect red and to not detect anything else.
Of course, yes,
Yep.
exactly.
Gotcha.
And so anything non-zero in these is bad. Anything non-one in this is bad. So you square all the bads and add them up, and that gives you a figure of merit, if you like, for this particular set of potentiometers of multiplier factors for a red Smartie. Still
A lot of
dubious.
variables there, David.
There's a lot of variables, yes. That's where an ESP will come in very, very handy. And it's possibly why the guy who did one driven with potentiometers being driven by motors didn't succeed terribly well. And I suspect he was trying to bite off a bit more than he could chew, because he had an array of 20 by 20 photocells trying to detect shapes. So this is a very simple problem in comparison, because it's just 3 input numbers and you're looking for the particular mix of 3 input numbers, red, green and blue. So have you got that idea about the error function? Yeah. Iqbal is brave, he's nodding. George, come on. Yeah,
Yeah.
okay.
I was holding my thumb up.
Sorry?
I was holding my thumb up. I thought you would have seen it.
No, I didn't see it before. Now I see it.
Okay.
Good. Okay, so move on. But that error function is kind of an important part of the deal. Very important part of the deal, because now we get to training and what the cognoscientists call backpropagation. And what we do basically in training is we present a Smartie, a red Smartie, and we note the error here, and then we just adjust the factors just by a tiny little bit. And if with a tiny tweak of that one there, that number gets better, good. Tiny tweak of that one, the number gets worse, tweak it back the other way, and hopefully it'll get better. But you only do a tiny little bit. If you do too much, you're going to drive it off the scale somewhere. So you do that with each of your Smarties, tweaking those coefficients many, many times. You go the red one, the blue one, the gray one, the purple one, the pink one, the orange one, tweak the things, and then you go back and you repeat many, many times. And eventually, if you're doing it, got a plug behind you, it's going to converge on a good set of settings for all these. And you will have a thing that can categorize the different colors of Smarties. Does that start to make sense?
Yep.
So we've gone from the very simple thing here, tweak those so it detects the turquoise, through to now having multiple ones that can detect the difference between 3 or 5 or 7 different colors of Smarties. And that's the key to it. Now so I've got here. I'll go to that in a moment. So if you do this, this is something I realized before I went away and started doing this study. I was visualizing having to sit there feeding Smarties into the thing all day long, pushing buttons and what have you. Then I realized that basically, if you just feed the Smarties in one at a time, store the readings, the raw readings, and store which output you want that pattern to activate, you can now run that set of data on it many, many times, because each adjustment cycle has to be small. So if you've got just one set of data off the Smarties and run it, I don't know, 1,000 times, 50 times, I have no idea what it's going to be. It'll probably depend on how many colors are somewhat similar with each other. It's going to tend to converge to the right solution. I would say I would also probably take several readings off each Smartie, because just the angle it is in front of the sensor and all those sorts of things will have an effect too. But with an ESP32, there's a fair bit of memory to store all this stuff, and the thing can crunch numbers pretty quickly. Maybe not as fast as a Raspberry Pi, but it's compared to the microprocessors that I did with most of my career, which was little 8-bit things running at 20 megahertz tops. ESP32 is a monster and got more memory than we can ever imagine using up. So I've got a feeling quite optimistic that it'll be able to work. The rest of the actual mechanics of the machine and so on, that's relatively trivial stuff by comparison, at least when I get my 3D printer fixed. So now the next thing is in the real world, they actually use multiple layers. So the one we've been looking at is basically one layer and two layers like that, but in the real world they use multiple layers. So 2 layers like I've had here can sort Smarties, but 2 layers like this can't interpret French and translate it into Hindu. It takes many, many, many layers. One of the interesting things I came across was, does anyone remember years and years and years ago, people were sticking electrodes into the brains of cats, and they were determining that the eyes, when it looks at patterns, there's a whole bunch of neurons that go off with horizontal lines, with vertical lines, with angular lines, and all that sort of stuff. And then there's a whole bunch of neurons that put those together to something that might be the beak of a bird or what have you. That was done many years ago. Then I came across something the other day where they were doing, using a functional MRI machine, were doing something similar to hearing. And they were for different parts of what was for just raw sounds. There was sort of a bunch of neurons quite close to the ears themselves that were going off, and then sequence of blah, blah, blah. And there were sort of several layers until you finally got to the bits deep in the brain that were actually picking out words and meaning. So something a little similar to this is actually going on in the brain, which is kind of awesome. So, something in, well, ChatGPT, one thing I came across was talking about ChatGPT, in fact, is not just multiple layers, it's multiple computers, sometimes all over the planet.
Yeah.
Right, so it's just, the scale of it is massive. And these things use a lot of power. They're talking about gigawatts into a computer center. Serious amounts of power.
David, at this point, have you talked about there being a feedback mechanism in this arrangement?
No, I haven't, and that is definitely beyond my Dunning-Kruger threshold, I think.
I was wondering whether I was jumping ahead, but obviously if you can color sense accurately, then you can have a feedback mechanism on this, and you could have some artificial intelligence applying itself to what it's seeing and enhance the output or the accuracy quite rapidly.
Yeah, look, the only stuff I've come across with that so far, Rob, and bearing in mind, I don't have a very good mathematical brain. So once they start talking about, or the big boys don't do it the way I've been talking about, just little tweaks of the pot. They talk about using partial derivatives, all the different functions in the chain, and literally chaining and calculating that way. For me, it'll be tweak it by 0.01 and see what happens kind of stuff. So a bit of a sledgehammer. So, and look, there are different levels of sophistication in this, and researchers are constantly discovering new and better ways of doing it just by mucking around, which I find fascinating. So it's it's obviously it's creative, intelligent, and explorative, I suppose you'd say, what's going on. The feedback, the only reference I've seen to feedback, and I'll qualify this in a moment, is basically the mechanism where they call it back propagation. And I think, to me, that term back propagation is a bit of a misnomer, because there's no sort of numbers being transferred backwards. It really is determining a minor adjustment on each of the factors and applying it until the output gets a bit better, as far as I can tell. Now, if we had someone here who's an expert on this stuff, you might say, David, you're full of bullshit because the Dunning-Kruger is raining. But that's what so far what I've been able to see. Now I did.
David, from a control engineer point of view, training is feedback. Simple as that.
That's a linguistic thing rather than okay. You and I think of don't we think of, well, I do, I think of feedback as wiring something through a resistor back to the input of the op amp type of feedback.
Well, that's pretty much what's happening here. You're looking at something and then you're adjusting something further back in the chain in order to get the thing at the end of the chain to move the way that you want it to. That's feedback.
Your brain is the feedback. It decides that's better or not better.
But you're trying to minimize the error or reduce the error with each pass of the feedback loop.
That's effectively feedback, isn't it?
Yeah.
Okay, well, look, yes, you could conceivably invent a machine or some software that would do that automatically. Which, in fact, I suppose is what I'll be writing. I think of it more as being a little bit of a suck and see operation rather than that. But yeah, okay.
This is Monte Carlo optimizing, isn't it, David?
Bruce?
Not quite. I spent a decade
on
writing
its
Monte
way, though.
Carlo simulation programs. It's not quite Monte Carlo because this is not really random.
Yeah.
Oh.
Yeah, that's right. Well, you'll have to tell us about that one day, George. Sounds fascinating. I've never really. No, I haven't in my career. I've not ever used that. I've also not used circuit modeling. That sort of stuff.
There's a reasonable amount of mass behind this, obviously, doing
Yeah.
Monte Carlo simulation. So
Yeah.
I'm not sure that many people would be interested.
Depends how mathematical you get.
You can't just drop all mathematics to talk about it, or at least I can't. I'm not a teacher.
I'm sure
Anyway,
you'd make it interesting.
okay, yeah.
Let's continue talking
yeah,
about Smarties.
That's for another day.
They're not random.
Yeah, thanks for that one, Bruce. Now, in my readings, I did actually come across actual feedback where the output of a neuron would actually be fed back as an input element to a previous one in the chain. And if you think about, I mean, the brain really is a great big, somewhat random soup of connections. So that makes sense that, I mean, it's not laid out to schema. It's sort of these little dendrites, what they're called, sort of go, I latch onto that. So it's going to be probably a lot of local and fairly global feedback loops taking place as well within the brain. How far the technology has come with that, I have no idea. Absolutely no idea.
David, could you explain this more? You lost me on these multi-layers.
Yep.
What's in each layer?
Basically, it's more of the same. Where are we? Yeah, it's more of the same. So this might be our RGB inputs, and then we have one layer like we've had before, and those outputs that output there goes to every one of the neurons in the next layer with a factor and so on, which is why at the end I started to draw one. And I thought, no, I bugger this, I'm not going to do. I'll find a ready done drawing. So I stole that off the net, that drawing there. So there's lots and lots of connections there. But the more layers you have, the more it's able to make subtle differentiations. So right up to the point.
What you call X1 and X2 is just two copies of that first layer you drew, but with maybe different settings.
I'm sorry, X1 and X2. Oh, this one only has 2 inputs. Mine has 3.
Oh, they're actual inputs. Okay.
Yeah, they're inputs.
They're sensors.
Well, they're sensors, they're eyeballs, they're little resonant nerves inside your ear.
Gotcha.
All right. There are other techniques for handling time sequences, which I know nothing about. You might conceivably imagine if you got a time sequence, if you feed it pass all these inputs in a shift register or something like that, or a delay line. I literally don't know. But the more layers you have, the more math you have to do, and it probably goes up, I don't know, as a square function or something. I've never thought about it. But the more subtlety you can get in your, these are all pattern recognizers, ultimately. The more subtle you can get in the patterns you can recognize. So you've got, one of the classic ones is something that can detect letters or numerals off an array of maybe 32 by 32 pixels or something like that, which might be an excellent, this sort of thing Iqbal would probably go ahead and do with a camera on an ESP32. You can, by the way, I almost said you can get, there's a library for the ESP32s and Arduino called TinyML, which I guess is something that will do this. You set it up. Have you played with it, Iqbal?
I actually haven't, but I've seen like a little object recognizer AIs running on ESP32s. It can like recognize your face and like chair tables, cats. So.
Yeah. I saw one guy on YouTube who was making a little wheeled robot with a ultrasonic sensor that was scanning backwards and forwards, and it was using an artificial intelligence. Not wholly successfully.
Excuse me, David, if I could just interrupt you. In the chat, Brian Davis is saying that he can't start the video. Is he waiting to be let in, or is there a problem at his end? If you have a quick look at the chat.
Yeah, no, he said he was couldn't get his video going, so he's just sort of that comment of his was at a minute to 8 or to 7 if you look. So
okay, yeah, sorry.
Give us a sign, Brian. Polite sign. Hello, Mr. Brian.
Let there be light.
Yeah.
Flash of a lid.
There we go. Something happened there. Yeah, he just came back to us.
Yes, I saw that.
Okay. Yeah, he's alive. We won't send help. Yeah, so look, John, sort of back to your question. You can add more layers, and the more layers you've got, the more powerful the thing becomes, basically.
Yeah, I can see now.
And the more computational power it will absorb, of course. Which was all the problem that Geoffrey Hinton had up until 2008, when suddenly, and I mean, he wasn't thinking about sorting jelly beans or Smarties for that matter. And to do something useful in the real world, he needed real grunt and lots of training data from the internet. So the internet actually contributed to that as well. So the question is, could it be done with an all analog thing? One of the Smarties sorting machine is one thing I want to do, and that's going to be the easiest one, I think. But I would love to build for the club a demonstrator where you can come along and twiddle a pot yourself and get it to learn how to even distinguish between a red and a green disc or something like that. So in 1958, Rosenblatt Mark I perceptron at Cornell University, he motorized the potentiometers. I mentioned this, I got ahead of myself before. I've seen it, actually I should have grabbed a picture of it. And he had this array of photocells, it was sort of about, where are we? Yay square. So it wasn't tiny little phototransistors mounted on a printed circuit board those days, it was big and clunky. And he attempted to be able to detect different shapes, but he was only using a single layer network. And therein lie the problem. You see, if you have a multiple layer network, sort of returning again to your question, the cat with the horizontal lines and the vertical lines and what have you, the first layer might do nothing but detect, shall we say, all possible horizontal lines. Sorry, categorize the basic fundamentals of the drawing of the image it's looking at. Horizontal lines here, vertical lines here, diagonal lines there, diagonal lines the other way there, circles, squares, what have you. And then the next one, combinations of those. So 2 horizontal lines and 2 vertical lines is a rectangle, that sort of thing. And how you make that one detect one sort of thing and that the other sort of thing, I have absolutely no idea. Absolutely no idea. Do you just say clever cat when you get an output there or what? I have no idea. And I won't be exploring that this year, that's for sure. I'm waiting for that next model of microprocessor that's costs $5, 64 bits, and it's got gigabytes of memory on it and runs at gigahertz. So he did that in 1958. Now, right now, there are neural network devices being developed based on analog electronics, such as memristors. If you don't know what a memristor is, I refer you to Google. And the thing about these, the coefficients for whatever the job is, which might be detecting little old ladies walking in front of your car, can be preloaded with coefficients in the factory. So it doesn't need to have that feedback and training mechanism in it. You use a digital network, you learn the coefficients to produce the performance you want, and then you just pre-program it into these analog gadgets. So at the end of the day, it could almost be as little as an array of resistors, a big array of resistors. But an analog circuitry uses a lot less power, seriously less power. And so does the brain. Human brain runs on about 30 watts. ChatGPT is probably consuming megawatts. You'd have to carry a very big battery around if you wanted to have a digital thing on the move. Having said that, I've come across headlines. I don't read them because I don't understand it, but they come across headlines in the technical press about chips being developed to provide AI in here. In fact, there probably is already, but we just don't know about it. That's one of the things. This stuff has actually been around and been in circulation for quite a long time, but we just haven't really been aware of it. When you say, "Hey Google, what's the weather tomorrow?" That's what's happening. So that's my last slide. And it's nearly 8 o'clock.